Welcome everyone. In this video I'm going to show you another type of magnetic position encoder. So in some of my previous videos I was working with magnetic position encoder, and that is this guy here, the AS5600. So this is a very simple construction, but it's a very useful construction. So we have a chip which contains several Hall sensors inside, and based on the displacement of a specially magnetized magnet, this small guy here, we can detect angular displacements, and then we can convert that into different kind of parameters like speed or angular displacement and so on, anything which is related to rotation. And then this guy is an I2C device, and it has a drawback that it has a fixed address. So if you are not using any kind of special circuits, you can only use one at a time at one I2C bus. And then of course there is a workaround for this, and I showed this in a video which you can see up there in that corner. So if you have an I2C multiplier or multiplexer, to be more precise, then you can use 8 or even more if you have more multiplexers with a single microcontroller. So this works very nicely, and it works very well, but sometimes you don't want to fool around with the I2C multiplexer, or you have other kind of restrictions. And then today's video will be about this small guy here. I just put it next to the AS5600. So this small guy here is the AS5048A magnetic position encoder. And the main differences between these two guys is that this one is 14-bit resolution, and this one is 12-bit resolution. For us who are working with, for example, stepper motors or something like that, it doesn't really matter, because these two resolutions are quite huge anyway. But this one, with the A at the end of its name, it has SPI connection. So you can see these solder tabs here, and actually those are the SPI pins. And the advantage of this is that if you use standardized SPI, then based on the status of the chip select pin of the certain unit like this, you can put several on the same SPI bus and then just select the corresponding detector or sensor based on which SPI pin is brought to low. So then, as I said, this has a slightly higher resolution. The theoretical resolution is 0.0219 bits, and the noise is maximum 0.06. So like 3 times the resolution, which is quite great. And usually when we are using some kind of small stepper motor with, let's say, 400 steps per turn microstepping, which is relatively a general setting, then you are just below 1 degree per step. So you can resolve the steps of a stepper motor easily with both sensors. So then in this construction here, back at the stepper motor, we have this nice little sensor. You can see the bolts here and the nuts, so they are holding the sensor against the shaft of the stepper motor. And at the back we have this usual small diametrically magnetized magnet. And then when the magnet rotates together with the shaft of the stepper motor, then we can register the displacement. So then in this video I'm going to show you how this works, and I'm showing it in a bit more practical way. And of course I will tell you the source code. And once again, the main difference is that the black thing here, which is the AS5048A, works with SPI. So what you can see here with a bunch of cables is just the standard SPI connections. And of course, on my website you will always see the correct wiring, but this top row here is nothing else than just the detector connected to an Arduino Uno to the SPI pins, the standard SPI pins, and then we have another 16x2 LCD which is just displaying a few numbers. And what we will see here is the RPM and the total angular displacement. So basically the accumulated turns times the degrees. And then to further elevate the demonstration, I finally assembled my small control panel into a enclosure, and it has some fancy connections for the stepper motor, which can be any kind of stepper motor with direction and step pins, and also with the enable pin, and then two other connections or terminals like this here for two limit switches. So for example, if you are using a linear actuator, then you can put one limit switch in the beginning and one at the end of the linear rail, and then you can program it in a way that it will act in a way when you hit the limit switch with the carriage. And then we have a DRV8825 stepper motor driver on a breakout board, and that's all. And why I have this separate thing here is because I want to run this stepper motor and then read the magnetic encoder. So this demonstration will be about this thing mainly. So then I plug in everything and I continue discussing this stuff. So now I plugged in this part, the top row, which is just the magnetic encoder. And what you can see is that the RPM is 0 because the shaft is standing still. And this is the total angular displacement. And then there is always some small uncertainty in the angle that we read. So that's why this number is sometimes jumping between 0, minus 0.1 or plus 0.1. But that has nothing to do with the device. It works nicely. So this is fixed. And now I just connect the stepper motor part and see what is happening. So power is connected, and then I connect the USB cable. So now this is also on. So what I'm going to do now is I will run the stepper motor here with 400 steps per second speed. And since I have the microstepping set in a way that I'm using the full steps, which is 200 steps per turn, then this means that in each second I expect 2 turns on the main shaft. And then if we translate that into RPM, that is 2 times 60, because we have 60 seconds in a minute, then the RPM should be 120. And you will see it in the code how I calculate it, but we need to wait some time in order to get proper numbers here, because we have to accumulate a certain number of turns to get proper statistics, and then we can calculate the RPM. But basically what is happening is that I'm collecting the number of turns for 15 seconds, and then that is like extrapolated to 1 minute. Basically I just multiply the number of turns by 4, and that's all. But this is not too accurate if you want to have like sudden changes in the RPM values. But if you have like a constant speed for minutes, hours or something, then the RPM will perfectly show you what is happening. So now what I have here is the speed menu. So I entered it, and then all I have to do is just press this button and start moving the motor. So now once again we will do 400 steps per second, so that will result 2 turns per second, which is 120 RPM. So now I just start this and we will see what happens. So the stepper motor started, and you can see that the total angle is increasing because the shaft is moving, and then the RPM started to increase. But as I said, this has to wait for like 15 seconds, or even better, let's see, say 2 times 15 seconds, so half a minute, because then we are sure that we collect the number of turns while the motor is moving with a constant speed. And now you see that we have already reached the condition when we have constant speed for at least 15 seconds, and then the RPM is 120 as we expected it, like theoretically. So then I stop the motor, and what we can do, for example, we can try this with a higher setting just to see what is happening with the RPM. Now I expect the RPM to drop to 0 after a certain time because the shaft is not moving, but since the averaging goes every 15 seconds, we still have to wait. So I doubled the speed. So what I expect here is that the RPM should be 240 if everything can work as I expect. So let's see. So the shaft is running. We have to wait a bit just to get like a consolidated value, and then we will see what is happening. And here you can see that the numbers are going in the negative direction for some reason, so I might have messed up some values which maybe overflow or something in the code, but when we go to the coding we will check it and we will try to troubleshoot it. But as long as it works, and as you can see here, the RPM is 240 as we would expect from the doubled speed. So just to go through the, let's say, mathematics of this thing, we say that we want to move 800 steps per second based on these settings. We have 200 steps per turn microstepping setup, which means that we are doing 4 full turns on the shaft per second, and then 4 times 60 is 240, which we see on this display. So you can see that it works properly. And just for fun, I will stop the shaft by pressing the limit switch. So we stopped. And then basically this was the whole demonstration. So you can see that this chip works exactly in the same way as this guy here. The only difference is that now we communicated with the chip through the SPI protocol, and basically that's all. The other details are not so relevant for us if we just want to detect the turn of the shaft. So this is pretty much it. So let's go to my computer now and see how the code works, and I will also try to find out why the numbers went in the negative direction. So let's go to my computer. So let's see how the code works. So in the beginning we have to include 2 libraries for this unit. One is for the SPI, so we can communicate with the encoder, and in the comments I put the SPI pins both for Arduino and STM32 Blue Pill. These are the standard SPI pins, so you don't have to define them as output and so on, except for the chip select, but these are standard. They are treated properly in the SPI library, so all you have to do is just to include the SPI library. And then we have the display, and I'm using this liquid crystal I2C library. And again, in the comments we have the SDA and SCL pins defined for Arduino or STM32 Blue Pill, so you just have to follow these pin instructions. And then we create one object, so we use the 16x2 LCD on this address. So now I define the pin directly for the chip select pin because we want to switch it manually. So then we say that it is on the pin number 10. As I said, I'm using an Arduino, so this is for Arduino. If you are using the STM32 Blue Pill, then obviously you have to switch the PA4 pin. So then we have a bunch of variables, and first of all we have the raw data which is coming from the encoder, and that is stored in a 16-bit integer, and then the rest is basically just float numbers. So we have the angle expressed in degrees. We have a starting angle which we read at the startup of the device, so this will be always subtracted from the angle because whenever you start the device it doesn't start at 0 degrees, but it shows you an angle based on the alignment between the encoder and the magnet. Therefore there will be always some certain number, I don't know, 15 or 273 and so on and so on. And then if you want to make this more readable or more understandable number, it's better to start from 0. So that's why I use this start angle. And then the corrected angle is basically the degrees angle that we converted from the bits minus the starting angle, and then we get 0 in the very beginning of the starting of the device. And then the total angle, that is just our accumulated angular displacement. So if you do, for example, 2 turns, then the value of the total angle variable will be 720. And then the number of turns is basically the number of turns of the shaft, whether it is negative or positive. Then you know that you went clockwise or counterclockwise based on how you collect the data, and so on and so on. And possibly I did the error here because previously I defined this as an integer and I used this variable in a division where I haven't cast the value into float, and therefore I got the negative number after a while when I increased the number of the total angle. So that's what you saw in the demonstration, and now I changed it to float and I tested it. I went up to more than 100,000 degrees for the total angle and it was running fine. So I think this was the error that I mentioned a few minutes ago during the demonstration. And then we want to count the revolutions per minute. So we have the RPM counter, which is basically the same as the number of turns, but this value is always cleared in every 15 seconds. And then at the end we calculate the RPM. And we have integers, which should be integers because they are just changing between 1, 2, 3, 4. So the quadrants are just the full 0 to 360 degrees circle divided into 4 parts, and based on how the shaft passes through these 4 quadrants we can recognize whether it is turning clockwise or counterclockwise. Therefore we can either increase or decrease the number of turns. I will show you how this strategy works. We have this command, which is basically just the read command, but I made it into a variable because the way we send commands through the SPI is basically similar, but we have to change the commands. So whenever you want to do something else with the encoder, it's just easier to modify this number and then you get the response on your serial, for example. Then we have 2 timers. One timer is for updating the value of the LCD. So basically we just print the new values. And then also the RPM timer is to estimate the RPM. So this goes every 15 seconds. And then after 15 seconds we can count how many turns there were. And based on that we can estimate the RPM. So this was all the variables. And then let's go to the setup. So in the setup we have the SPI begin. Of course we have to start the SPI, And then I used the serial port to debug everything, and I kept those parts in the code, so you can also receive these numbers on your computer if you want. But what we have here is that we just start the serial, and then we just print some kind of message just to confirm that there is a connection between the microcontroller and the computer. And then, as I said, we will manually switch the chip select pin, so we have to make it as an output. And then this is a general copy-paste code, so we just initialize the LCD, the 16:2 LCD, and then we put the cursor in the 0, 0 position, so top left corner, and then we print the first line, and then we put the cursor in the second line or second row to the first block, and then we print again something, and then I wait. And then in this print LCD function, which I show you later, we just print the permanent parts on the LCD, so those parts which do not need to be updated every time, so we sort of save some resources. And just to check what's the initial angle when we started the device, we read the register which returns the value of the angle read by the encoder, and then that angle becomes the starting angle. So if the position of the magnet was 320, then that becomes the start angle, and we will use that 320 degrees to correct all the upcoming readings. So then here comes the loop. So what we do here is basically we read the register, we correct the angle based on the start angle, and then we check the quadrant, so we know the direction of the turns or rotations. We also know the number of turns, and we also know the total angular displacement. And then after these things are obtained, then we check our first timer. So if there are more than 250 milliseconds elapsed, we send some data to the serial, and also we update the LCD. And the update LCD differs from the print LCD in a way that the update LCD only updates the numbers which we want to refresh, so the text is never updated in this function. So again, it's just saving resources. And after everything is completed here, we read the current value of the millis again and put it in the timer. So this sort of resets this kind of timing, and we have to wait another 250 milliseconds in order to be able to step in here. And this is much better than the delay, of course, because then we let the rest of the code to be performed. And then another timer, and this is for the revolutions per minute counting. So if more than 15 seconds elapsed, then we enter, and what we do here is that the RPM is basically 4 times the counted number of turns in 15 seconds. So then why it is 4? Because we just calculate for 15 seconds, but we assume that the speed is constant, so this will be valid for the whole minute. 60 seconds divided by 15 seconds is 4, so the currently counted turns times 4 should estimate the RPM for us. And then we have to reset this, because if the speed changes, of course we want to count over and over, and therefore this has to be reset, so a new clear value will be determined. And then of course the timer is also read and reset, so then we do not enter here for another 15 seconds. So let's see how the communication goes between the microcontroller and the magnetic encoder. So we start the SPI, MSB first, and SPI mode 1, that is very important. And then first we send a command, and we use the spi.transfer 16, so we do not send 8 bits but 16 bits at once, and this command was the one that I showed here. So we send that to the magnetic encoder, and then we wait a little bit, and then we send the command again, which will sort of shift out the data for us, and we read that. So the result of this command will result in receiving a 16-bit number. And then we know that we have a 14-bit number, which is useful for us. So what we have to do is we have to remove the top 2 bits. And why? Because there are different things stored in the top 2 bits, and if you add them to the number that you want to interpret as the degrees angle, you will get very funny values. So with this bitwise AND operation, what we do is that wherever we have the ones, which is just 14 bits, we keep that number from the raw data variable, which is the reading from the register of the magnetic encoder. And that will result in a 14-bit number at the end. So we just cut off the pair and the EF variables or parameters, and then we have the number. And what we do here is that we calculate the angle in degrees. So we have the raw data, which was an integer, so we cast it into float, and then we divide it by 2 to the 14th power and multiply it with 360, which is the 360 degrees, and this will give us the angle position in degrees. And if you want, you can send this to the terminal. I skip it here because I use the display. So now we read the degree angle, so we have to correct it, and what we have here is just we recalculate the new angle, so this will give us 0 in the very beginning. So what we do here is that the corrected angle will be the degrees angle, which we just recently read, minus the starting angle. So this sort of tears the position. And also we have to do another correction, that if we have a negative number, that's not so good if the corrected angle is negative number, because the full circle for us will be starting from 0 degree and ending at 360. So if we get a negative number, that will not make any sense on our circle. So what we have to do is that we have to put it on our circle. So for example, as I show here in the comments, that the minus 15 will be the plus 345 position. So that's done, and if we want to make sure that we have the proper angle calculated, we can print it on the serial port and check it. And then we have the quadrants. So this is, you can imagine this as a circle, and then we have the different quadrants. So you can see these 4 sectors, and they are defined here, how they look like. And you see that if the angle is between 0 and 90, we are in the first sector. If it's between 90 and 180, then we are here, and so on and so on. And then we see that if there was a change between the quadrant numbers, so the currently determined number is different than the previously determined value, then we enter this part and we see 2 different kind of transitions, and what we see is basically this transition. So if we went from the 4th quadrant to the first one, then we know that this is our clockwise rotation. This is how we determined it. So then we increase the number of turns because we did 1 full turn in the positive direction, and we also increase the RPM counter value, which will help us to calculate the revolutions per minute. But then if the opposite happened, so we was in the first sector and we are now in the 4th one, then we went counterclockwise in our coordinate system, which means that we have to decrease the number of turns, and also we have to decrease the RPM counter. And this is very useful because if we are turning counterclockwise, then the negative sign will indicate us that this is the opposite direction that we defined as the positive direction. So this is a nice thing. And of course we update the previous quadrant number, so whenever there is another change we will know that something happened. So we print the numbers if we want. And now, since we have the number of turns, we can calculate the total angular displacement. So this is number of turns times 360. So this is basically just the number of turns. And then we add the corrected angle, which will determine the current position on the absolute scale. And of course, when the number of turns is 0, then this whole term is 0, and we are in the circle somewhere. But then when it becomes 1, then this becomes 360 because we did one full turn already, and we add this. So for example, if we did one turn and we did half a turn more, that will mean that this is 360, this is 180, so the total angle should be 540, and so on and so on. And then this is now printed on the serial terminal. Of course, if you want, you just remove these comment symbols here, and then it will end up on your computer. And this is done. And now what we do, the rest of the stuff is just printing on the LCD. So the print LCD is the permanent part. So what we do is we just print the RPM, and this part will never be changed. But then we just print the numbers in the very beginning as some kind of placeholders, so they will be initially 0, of course. But what we do is that we move the cursor after this RPM text, so actually the cursor will be here where you see it blinking, and then we erase the rest of the screen, and then we move back to the beginning of this erasing part, or erase the part, and we print the RPM value with 0 digits, so it will be just an integer. And then we jump to the second line and we print the text again, and then we put the cursor after the text and we erase the rest of the display, and then we display the total angle with one extra decimal. So then, yeah, you see if it was 300.2 or 200.7 and so on and so on. So this is done, and then we come to the update LCD part, and technically what happens is that we just update the relevant parts. So we jump to the fifth block of the first line, we erase some space here, and then we jump back to the beginning, so we jump back basically here, and then we print the number. And then the same happens with the total angle. So we jump to the second line, to this seventh block, and then we erase the space. We jump back, because when you erase or when you print, after the printing, the cursor will stand at the end of the printed text. So we have to put back the cursor here, and then we print the total angle with one extra decimals. And that's all. And this goes over and over in the main loop, as you can see it here. So reading, correction of the angle, calculating the rest of the values, and then if the timer is updated, or when the time elapsed that we need, then we update the information on the LCD. And then this goes over and over as long as you run the device. And then if you want, you can update this into a quicker interval. So let's say you have this as every 5 seconds, but of course then you have to multiply it by 12, because 5 seconds times 12, that will give you the 1 minute, or anything that you like. But of course, if you update this more frequently, then you might lose some precision. But for me, it doesn't make sense to update it quickly, because if your RPM value changes up and down very rapidly, then I think you should not rely really on the RPM value, but maybe on some other value. For example, angular speed or something like that, and that you can also calculate based on the information that you got from the encoder. So basically this was all. As you can see, this code is not so complicated and it does not really differ from the AS5600 code. There we use the I2C but employed the same let's say strategy to calculate the angles and so on, and the result is basically the same. The resolution doesn't really matter for us, I think, because it's just too fine resolution anyway. So if you work with stepper motors, for example, that plus minus 0.2 degrees or something like that will not really matter anyway. And what I also have to mention is that this device is much more expensive than the AS5600. So if you don't have any special reasons to get this device, then you should stick with the AS5600, and in the worst case you have to use the I2C multiplexer, but still with the addition of that thing you will get more value for your money. So then this is the end of the video. Please don't forget to visit my website curiousscientist.tech, link in the description as well, because I will publish this code there, and I will also publish the wiring if you need it for some reason. And then also you can look around on the website because there are other useful information, hopefully. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.